So good morning, everybody. My name is Fabio Iocco. I used to be a professor here. I'm still am for a very short time, next 2 weeks, and then I'm moving somewhere else. Welcome to the ICTP-SAIFR. This is an institute which was started a few years ago to bring excellence, some scientific excellence in the field of theoretical physics and related fields here to South America to coordinate a little bit the activities, and it's a spin-off or a Son Institute of the one that is in Trieste. I don't know if you heard about it. You can read more about it. So the idea of the institute is to organize mostly workshops and conferences as acting as a network point. So to bring people here, it's easier than bringing people to Trieste or somewhere else. So this school sits in that idea of creating a program about a specific subject and having people absorb it in local with experts from all over the world. And you actually have several experts here on the subject. All the professors that came here are very well-known personalities in their field. So, and to a certain extent, I think you should consider yourself lucky that you're listening to their classes. I would have hoped to hear such classes when I was a student. And so I would strongly suggest you to use them as much as you can. That means ask questions, don't be shy. There's exercise and discuss sessions. So if you have questions that don't pop up to your mind during the class, write them down and bring them out to the discussion session. If you're too shy to ask them personally, write them down and leave a note on the desk when nobody sees you. But the idea is that you're not shy. We will try to make you not shy, and please ask. There's a camera, okay? So leave it to the secretary and ask for silence from the secretary, okay? So really ask any sort of questions that pops to your mind, even in terms of career advice or what you want to do or what the field is going, in which direction it's going. This is something you should consider, that is not just the technical questions, but any sort of question that may help you to grow as a scientist, okay? This said, with great privilege sometimes come great obligations. This is public money, so whomever of you is going to be paid for coming here, either from their own universities or from ourselves, is making use of resources that come from the public. And I do strongly believe that there is a moral obligation with that. Not only with the people that is giving you the money, which are people that are paying taxes, but with the students that are out because you're in, okay? So there's times to the classes, and there's a certain number of classes. We will take presence sheets, and those sheets have to be signed within 5 minutes from the start of the class. You have to be on time, okay? If you don't collect 85% of the classes, you won't be listed as present in the school, okay? This is some obligation that I think it comes with the privilege of being here, and I do strongly believe in it. Don't feel aggressed, but that's the way things goes, okay? This said, beside the small details, we would like to make this environment as comfortable as possible, okay? So if for any reason you feel threatened or aggressed or inappropriately addressed by someone else, either us or other students, you can come privately and talk to me. And if you don't feel comfortable talking to me, you can talk to Mab, that's standing up right now, that is going to be taking complaints. Nothing of the kind has ever happened, and I'm pretty sure it will not happen, but if it happens, I hope you feel comfortable that you are somehow protected, okay? This said, let's get to science. Practical thing, poster sessions, okay? You can hang your posters upstairs. I hope you've done it already. They will be standing there for the next 2 weeks, all right? And we're gonna go through it, but then there is a dedicated poster session on Wednesday on which we will put specific attention. And before that, you will be welcome to discuss very briefly, just to flash, 2 slides and say, okay, my poster is about this. 2 minutes, no more. And please give me, so come to me tomorrow morning and or today with your key, PDF key, and call the file your last name, he poster.pdf, okay? I will list them in alphabetical order as you put your last name, okay? So you're going to be called like that. And so on Wednesday, I will collect them on my laptop. We quickly go through the oral session, and then we go to the posters. There's coffee breaks, and what else? I am pretty sure I've forgotten something that will pop up. This is my own timer. Classes have to be on time. So let me go quickly to the very last point. The school is about a field that is very ripe, that has been giving a lot of results throughout the last 2 decades, but especially now is exploding. You might have heard about the multi-messenger evidence in the last years. Instrument CTA, just to mention one, is about to come online in a few years from now. It's been built. And there is one point that is important to me. The Southern Hemisphere is very relevant for this field, and we are in the Southern Hemisphere. Let's have a little bit of pride about this, and let's try to carry things forward from our side. This said, I leave you to an amazing lecturer, Pasquale Blasi. Pasquale had his PhD from the University of L'Aquila, which is in central Italy, close to the Gran Sasso, some time ago. I don't know when, I don't want to know. Then he went for postdocs at the University of Chicago, then Fermilab, and then he went back to Italy, where he was a staff professor at the Arcetri Observatory, one of the 2 observatories of Galileo Galilei. And then he recently became full professor at the Gran Sasso Science Institute, which is in L'Aquila again, but it's a brand new institute and it's an amazing place. So it's my pleasure and my honor to have Pasquale start his classes.
So I need to push this thing to be followed, right?
Yes, and the microphone to be on.
The phone is on.
Just one last point. We encourage you to ask questions in English, okay? But if you're really not able to formulate your question in English, I will translate for you from Spanish and from Portuguese to English, okay? But try and do it in English. But if that's breaking, it's putting a wall between the science and the thing, that we prefer that you ask the science and you keep the language second.
So thank you, Fabio, for the great introduction. Is this on? And it's a real pleasure to be back in Sao Paulo. I've been here several times, mostly for schools, actually. And it's a great place to be. So this is, I was asked to give the first lecture of this school as a sort of general introduction to the field. So this is a very introductory lecture to basically all the courses that you will hear about in this school, okay? So its purpose is not to provide technical details about things that will be discussed. That will start later. And in fact, this will be, I believe, the only lecture that, at least of my lectures, that will be on slides. The rest will be at the blackboard. The purpose of this lecture is really to provide a sort of big picture of the field, where it was, where it is, and where I think, or we think, it might be in the future. So it is really like brushing through the different topics that might be of relevance for the students. Now, the school is a school of high-energy astrophysics, and that is a pretty broad area. What is it? I mean, there are some of you that probably already started working on gamma ray bursts or supernovae or cosmic rays or gamma rays. All of these things pour in the field, and sometimes it's a little bit difficult to understand the boundaries of what we are talking about. Now, I think that despite these boundaries are kind of fuzzy, there are a few topics that are really fundamental for all of these things. So the purpose of, at least of my lectures, and I believe the lectures of Professor Serpico, will be to provide those bases that will be usable whatever is the thing that you are working on, for the reasons that I will try to explain. I'm not sure what the list of the topics provided on the website is, but we agreed with Professor Serpico to split the things in such a way that I will cover more of the part on particle acceleration, and Pasquale Serpico will cover more the part about cosmic ray transport, or transport of particles, of high energy particles in the universe, whatever that is, okay? So let's start from the basic question. Why are you here? So what is that? What is the main purpose? Well, throughout different fields, throughout the different studies of the universe, you see evidence that there are many, many non-thermal activities in the universe, okay? Many, many that go from supernovae to gamma ray bursts to cosmic rays to gamma ray observations and so on and so forth. So there are many, many fields that are connected to what we will be discussing about. But I would say that if I had to choose, I would identify two big questions that are at the very bottom of all of the things that you will learn through your career, not only through your study, through your lectures here. All the non-thermal phenomena that you will ever study bear down to two big questions. One is, how does nature accelerate particles? Namely, how does it happen that a few, very few particles from the thermal pool are promoted to become accelerated particles? How does nature decide that? And how does it achieve such a purpose? This is the first question. The second question is, once these particles have been produced, how does it happen that they move, they get transported both inside the source in which they have been accelerated and from the source to either the Earth or the place where you see them because of interactions? So these are the two big questions that we have to deal with. Of course, on the way, while you try to understand the answer to these two questions, you will have to deal with all the implications of them. For instance, these particles emit radiation. These particles suffer energy losses, and so on. And this part will be covered by Professor Serpico. Now, one thing that, again, I want to stress, as I said in the very beginning, these questions apply in the same identical way to whether you are interested in solar physics, supernovae, active galactic nuclei, gamma ray bursts, clusters of galaxies. All these sources, independent of where you look at, show evidence of non-thermal activity. All of them, from the solar system on, which probably means, this is subject of investigation, but this probably means that really the way that the universe creates a plasma, a generic plasma, is automatically associated also to the production of non-thermal particles. They just come for free once you produce a plasma, for instance, inside a cluster of galaxies or inside a supernova or wherever else. And this connection needs to be, of course, investigated. Before, Fabio Iocco was mentioning the issue of asking questions in English, and so all of a sudden a doubt popped in my head. If I speak too fast, or if I'm saying something that you don't understand, please stop me and I'll repeat it, okay? Now, as I said, while these particles are getting accelerated, for instance, they interact with the environment and they generate secondary particles. This is one extremely important part of what we do, of what we study, right? Because for two reasons. The first reason is that this radiation can be used as a probe of our theories, okay? So if you have a model, a theory of how particles get accelerated in a source, how do you know if that is true, if the source is tens of parsec or tens of kiloparsec or megaparsec or gigaparsec from you, right? So you want to use probes which mostly have to do with carriers, with particles that either photons, neutrinos, or charged particles that get to you from that source, and that's the way that you can check your theories. Not only that, but also these processes that lead to the production of secondary particles also modify the way that both acceleration and transport takes place. In other words, you have to account for energy losses of these particles, okay? And this is part of the same game. The secondary particles that usually we deal with are, of course, mainly photons. And there are a few channels of interactions that are default kind of processes for the production of electromagnetic radiation, at least the non-thermal one. Mainly synchrotron radiation. All of these will be covered by Pasquale Serpico. synchrotron emission, so radiation of an electron mostly, but a proton as well, in the magnetic field, inverse Compton scattering, Bremsstrahlung, and the decay of pi zero neutral pions. By the same token, the charged pion decay will lead to neutrinos. There will be several lectures on how to use neutrinos to go deep into some of these sources, like gamma ray bursts, for instance. Electrons and positrons, at least on galactic scales, they are produced by the decay of charged pions, and at least on galactic scales, they are an invaluable probe, especially of cosmic ray transport, as probably Pasquale will talk about. And the same is true for antiprotons. Antiprotons are produced by inelastic hadronic interactions. So all of these things independently are probes of the two big questions that I told you before. How do particles get accelerated, and how do they get transported from A to B? Okay? And sometimes, it's not like in particle physics. In particle physics, you have an accelerator, you have a beam, you shoot the beam, you splash the beam on something. There are billions of particles coming out, but every single step is under control. In astrophysics, this is not the case. So sometimes you have to deal with what is usually called circumstantial evidence. So you put together a lot of different pieces of information, and you hope that all these different pieces of information fit together in a picture that makes sense. And so you can say, okay, you know what? Now I'm sufficiently convinced that what I'm seeing, I understand, and it is due to this or this other effect. Okay. One point that is very important, I mentioned it already a couple of times, the radiation that is produced by the particles while they are being accelerated or transported at the same time change the spectra, for instance, of the particles that are being transported. So this becomes, again, part of the same game. Now, it is often said, and actually even in the opening remark of this call, it was written that recently neutrinos and gravitational waves have opened the multi-frequency, multi-messenger era. This is good for journalists, it's great, but we are scientists, and we know that this has happened a long time ago, okay? Astroparticle physics is actually an intrinsically multi-frequency and multi-messenger field. By construction, it has been built because of that, okay? It has been built because of the power that we get in understanding the universe by putting together gamma rays with neutrinos, different messengers, of course, but also cosmic ray protons with positrons or with antiprotons. These are all different messengers, and you see radio emission and you see ultra-energy gamma ray emission, different frequencies. So an approach which is multi-frequency and multi-messenger is at the very basic of astroparticle physics since its creation as a field. So I don't think that this is something that happened recently. What happened recently is that it proved to be a right thing to do, to invest in this field, because even when you add to the list of the messengers also gravitational waves and neutrinos, well, great, it still works even better. With a few things to keep in mind. For instance, gravitational waves give information, of course, on the environment in which some events happen. For instance, mergers of neutron stars or mergers of black holes. It does not provide direct information on the non-thermal part of these phenomena. So some care should be taken there in distinguishing the two different things. A different situation for neutrinos, which are intrinsically of non-thermal nature. Again, I gave you some instances here, and some of you that might have already heard some of these topics. Positrons, for instance, and antiprotons and secondary nuclei are considered as the standard probes of cosmic ray transport, at least in the galaxy. For decades now, people have been doing these kind of studies. And not only that, but people have been using positrons to test some possible viable models of dark matter annihilation. So again, how to use these different probes, different carriers, to get information about some different piece of physics. Not only that, but gamma rays, not only from sources themselves, but sometimes even more important, from the diffuse emission from either our galaxy or the universe at large, contains a huge amount of information about non-thermal part of the universe. Radio emission has been used for decades as a probe of both cosmic ray acceleration and transport. Many places, supernova remnants, in clusters of galaxies, this is a key kind of observation. And now, of course, there is the issue of so-called new physics. This is something that, again, pops out very often. We want to discover new physics. We are pretty sure that new physics is there, and there are good reasons to believe so, because there are some of the things that we see that do not fit together very well, and that's, I think, great. But I think that historically, this is based on the fact that many new particles were, in the beginning, detected in the cosmic radiation. And so we sort of retain a little bit of trust that this may keep happening. Remember that many of the particles that now give for granted, like pions, kaons, several hyperons, and so on, positrons, were actually discovered in the cosmic radiation. So cosmic rays have played a gigantic role in the beginning of the so-called history of the Standard Model of particle physics. And so we are, as a consequence, still trying to adopt the same approach and maybe use cosmic rays to find signatures of, or hints of new physics. And you search for these things in the form of anomalies. What does it mean? That you expect, based on some model that you call standard, in the sense that you trust that it is correct, you describe the general phenomenology of the field, for instance, in cosmic rays, and then every single piece of observation that does not seem to fit exactly in that standard model, well, you can at least ask if it is sufficient evidence to think that there is something else going on. And this is a generic procedure that, again, worked fine in the past. Now, a few instances are, for instance, the positron ratio, which is the ratio of the flux of positrons to leptons, or electrons plus positrons, which is expected to behave in a certain way, you will see with the Pasquale cervical in the standard model. Namely, when you increase the energy, it should go down, and then you measure it, and it keeps growing. So there is an anomaly there in the sense that there are things that we don't understand compared with the standard model. Now, of course, the issue is always how well I understand the standard model so that I can trust that what I'm seeing is a real anomaly, or it's just a piece of the model that I put together that was wrong. So there is always a careful discrimination that one has to do between understanding the anomaly and understanding the possible new physics that might kick in at some point. And in fact, 99% of the times that we thought there was some new physics, it was not. It was just something that we didn't understand in the first place. But the same philosophy happens to antiprotons. For instance, antiprotons have been used, I'm giving you just instances, examples. Antiprotons have been used in the past as a powerful probe, for instance, of evaporation of black holes. There is plenty of emission in the form of antiprotons when a very small mass black hole radiates away its mass in the form of Hawking radiation, and it was expected for a long time to reflect into an abundance of antiprotons. We don't see it, therefore you can put a limit on how many black holes or the mass of the black holes that exist in the universe. One prominent example of this kind of technique is the gamma ray observation, the gamma ray emission from so-called annihilation of weakly interacting massive particles, which are the prime candidate for dark matter particles. Again, when you want to see this signal, which is intrinsically subdominant compared with the emission associated with normal cosmic rays, you need to understand the physics of cosmic ray, both acceleration and transport, very well so that you know what to expect in the standard model. And then once you know that, you can check if there is any anomaly. Another instance is the synchrotron emission from leptons produced in the same reaction of WIMP annihilation. These, the leptons, especially electrons and positrons, are supposed to be produced in WIMP annihilation, but also result in synchrotron emission. And this is something that has been discussed for many years now. And so the idea is that you have a WIMP that interacts with its antiparticle and eventually gives quark anti-quark. These particles hadronize, and the decay of pi plus and pi minus leads to electrons and positrons. And in the presence of a magnetic field, the emission of these guys ends up in the several gigahertz photons. And this is the same frequency as the cosmic microwave background. So in principle, if you look for cosmic microwave background anisotropies towards the center of our galaxy, you should be seeing something anomalous, or from clumps of dark matter distributed through the galaxy. So again, this is another channel through which you can use physics that you will hear about in this school to learn something about potential dark matter candidates. Finally, one instance that is now history is concerns the ultra-energy cosmic rays. When I started, actually during my PhD, which didn't happen that long ago, well, it was 97. I guess it was a long time ago. So there were two experiments, Agaza, a Japanese experiment, and HIRES, an American experiment, American-Japanese experiment, and they were getting to... North America. Say it again?
US, North America.
Okay, North American and Japanese experiment, which seemed to have discrepant results. So one of them seemed to see a feature that I will discuss in the end of the lecture, and the other one didn't. And the fact that Agaza experiment, the Japanese experiment, there is no ambiguity there, right? Okay. The Japanese experiment was actually seeing an anomaly compared with what they were expecting, led to the explosion of a field of investigation associated with so-called top-down models of cosmic rays, ultra-energy cosmic rays, mainly associated with the production of so-called topological defects, namely results of phase transitions in the early universe that led to the production of topological structures in the universe that eventually annihilate or decay at a later time. And there were a plethora of topological defects that came out with weird, interesting names even, Wimpzilla, necklaces, monopoles, and many other topological defects. I remember I was working with my supervisor, Benjamin Sergeyevich Berezhinsky, on one of these things, and we called them in a very sober way, super heavy dark matter. And then I went to the US, where I said it right? This is okay. So I went to the US, and there, they like much more to spectacularize things. And I was working with Rocky Kolb, and we wrote a paper on the same thing, but he used to call it Wimpzilla because of the Godzilla kind of thing. So Wimpzilla. And then I went back to my supervisor, Venya, and I said, I wrote this stuff on Wimpzilla. And he told me, Pasquale, what do you mean Wimpzilla? It is called the super heavy dark matter. And he was right, but anyway. Okay, so I want to go back to what I said before, namely that historically, a lot of what we call new physics, or what we call standard model today, but was new physics at that time, was actually found in cosmic ray stuff. So it is useful for our own clarity and sanity to go back in time a little bit and think about how things evolved from the very beginning. How did we get to the present time of knowledge of these things, okay? And actually, interestingly, the physics of cosmic rays starts in the end of 1700, although it's not always recognized. And there was a kind of observation that was very weird at the time of Coulomb and later Thomson. So Coulomb found that if you have an electroscope, you have seen electroscopes, right, in laboratory, I guess, or archaeology or something. But so you know how they're made. There is a stick and 2 leaves, sometimes gold, at the edge, at one end, and at the other end there is a ball, and you brush something like bakelite on your jacket, and then you put it close to the electroscope, and the leaves depart. That's the boring part. The less boring part is that when you take the stick out, the gold leaves go back. And they shouldn't, right? Because the charges should stay there. If they have been put there, they stay there. Where are they going? Clearly, if the charges that were there are no longer there, it means that there is a current. A charge that is moving is a current. So there was a current taken away from the electroscope. And so people were wondering, how can it be that you have a current in something which is so boring like the atmosphere? It's not ionized. It shouldn't, at least. So how do I get a current? And so there was a lot of discussion about this. It was clear that to some extent the air was actually ionized by something. But this something was supposed to be extremely energetic to produce the level of ionization necessary to explain the leaves going back to their rest position. Okay? So it became a big question. What is the source of this ionization? Now you have to understand a little bit of the historical context. In the end of 1800, basically nothing happened until the end of 1890 when people Röntgen discovered X-rays. In 1896, Becquerel finds that radiation from the decay of uranium also discharged electroscopes. So if you put a little bit of uranium close to the electroscope, the phenomenon is faster. And so people, it was the natural thing to think, right, that maybe what we are seeing as a form of ionization of the air is the result of natural radioactivity. Stuff that is in the walls is decaying. We know that this is happening at all times, so maybe that's the source of the ionization, and that's the reason why the electroscopes get discharged. And I would say that by the end of 1800, everybody was really convinced that this was the explanation of the phenomenon. And then there was a guy, which is usually completely ignored in the literature, probably because he was Italian and not German. And his name was Pacini, Domenico Pacini. He was actually a professor in the University of Bari in south of Italy. And he had this question. He said, well, what happens if I take my electroscope somewhere down in the water, deep in the water? Well, it was not completely new. I mean, the idea that you could take your electroscope and put it in different conditions was already there. Like, for instance, people tried to reduce the amount of air from the place where the electroscope was located. So what he said is like, let's see how it changed with the level on the sea level. And, well, he did these experiments. And Pacini's measured that the level of ionization is lower, 3 meters underwater, than it is on the surface. And so he says, well, how can it be if I go underwater that the level of radioactivity should be lower? It doesn't make sense. So probably, really, this source of ionization is something else. And he stopped there. So he did not go further into speculating. That's when it helps to be a theorist. When they speculated about what else could it be, no? And this, until a few years later, this guy, that was an Austrian guy, at 6 a.m., August 7, 1912, from Aussig, Austria, he decided to take a stroll on a balloon. A dangerous stroll, in fact, because he went up to more than 5,000 meters without equipment, and he actually felt sick out of it. But from the technological point of view, this development was due to the invention a few years before, 1909, of the Wolf electroscope, which was different from the leaves it had a little bit of a loop that changed shape depending on the level of ionization. And you could actually measure on a scale the level of ionization. So you took one of these things on board the balloon with a couple of helpers. And this was the breakthrough. So he was trying to do the same thing as Pacini, but instead of going down, going up. So this is what he saw. The level of ionization actually moving to about 1 kilometer above sea level drops. So he said, well, the idea that it's a radioactivity works. It is going down because I'm going up, and I'm getting farther away from the Earth. And then he went to 2,000, and then to 3,000, then 4,000, and more than 5,000 meters, and the level of ionization popped up a lot. So clearly, the level of ionization was not only, at least, due to the radioactivity of the Earth, but was due to something else, okay? And that's where he started speculating about the cosmic origin of this radiation. And contrary to Pacini, that was ignored by history, he got the Nobel Prize. And that's where the theories come in. And that's also when they make wrong conclusions. And that's something that you should always be careful about. When your theory fits the data, does not mean that that is the right explanation of nature. It's a good hint, but then you need other independent things. So what he did is something that, again, made sense. Millikan used the Dirac theory of Compton scattering to describe the propagation of gamma rays through the atmosphere because he thought that cosmic rays were gamma rays. And so what else could you do? You have the only theory existing at the time, Dirac theory, and I use it to describe what I see. And they said, okay, let's assume that there are different energies of the gamma rays, and I want to fit the observations in terms of different energies of these gamma rays. And he found that actually you needed gamma rays at these specific energies, 26, 110, and 220 MeV. And then he compared this with the binding energy of some of the elements in nature, because it was just found out that it was late 1930s, 20s, started to think about the EMC square and so on, right? So maybe it's putting together nucleons that liberates this energy. And then look at the coincidences. If you put together 4 nucleons to a nucleus of helium, the energy liberated is 27 MeV. It's like, whoa, this is the so-called, that's when he came out with the theory of the birth cries of elements. So he thought that these gamma rays were the birth tears of elements just being born in the universe, throughout the universe, because of nuclear fusion. And then you put together 14 nucleons to put add nitrogen, it's 108, which is pretty close to 110. He didn't bother about carbon. And he didn't bother about oxygen, but then there was silicon, which was pretty close to this 220. And so with a little bit of jiggling around, well, he concluded that the gamma rays were actually the birth cries of the elements in the cosmos. And this was the accepted theories for cosmic rays for quite a while. And Millikan is actually responsible for the invention of the name cosmic rays. That's why we call them cosmic rays. Rays, usually in our language, means gamma, means photons, right? So we call them rays because of Millikan. And now we know that this is completely wrong explanation of what happened, thanks to this other guy, an Italian, Bruno Rossi, who worked in Arcetri for quite some time. And he thought, well, if these are gamma rays, they shouldn't be able to cross blocks of lead. If I put several of them on a tower, and then I put Geiger counter in between, the Geiger counter had just been discovered, I should not be seeing gamma rays going through. So the lead should stop the gamma ray. Not only didn't stop the cosmic ray, but actually crossed several of them in a tower, which meant that A, they were not gamma rays, but B, the energy was much larger than the 20 MeV or 100 MeV that we're talking about. They're certainly larger than a GeV. So this was the discovery that cosmic rays were not gamma rays. And soon later, he came out with a possible experiment to be done to make sure that cosmic rays are whether positively charged or negatively charged, right? So he proposed the so-called east-west effect, namely because of the magnetic field of the Earth, positive charges are deflected in one way, negative charges are deflected the opposite way. So if you're sitting in certain locations on Earth, you should be seeing more cosmic rays coming from one direction rather than another. In 1931, not him, but Compton made this experiment, and actually Rossi only repeated the experiment in 1931, showing that most of the particles were positively charged. And so most likely these cosmic rays were actually protons, certainly not gamma rays. Well, this was a bit of the beginning of a race towards two things. On one hand, finding new particles. 1932, I believe, Chadwick discovers the neutron. 32, Anderson discovered the positrons, all in the cosmic rays, okay? And then 34, Rossi finds evidence for extensive air showers, namely several detectors in different locations hit by particles coming from the same shower of particles induced by the same cosmic rays. Niedermeyer and Anderson discovers the muons, and so on. So you can see two things going on in this decade between the 30s and the 40s, right before the Second World War. One was the discovery of new particles, again, positrons, neutrons, the kaons, pions, several hyperons, and so on. And on the other hand, the energy detected in the experiments that were getting larger and larger in size was higher and higher. So at some point during this decade, people started wondering, well, for sure they had understood that there was non-thermal universe because all these particles were impossible to accelerate on Earth, and certainly not easy to figure out how to accelerate them anywhere else. But also, they started wondering what limits this phenomenon. At some point, is there a criterion that limits nature from accelerating above some energy? And it really didn't seem so until the end of 1960s, because the energy went up and up and up. And in fact, you can see that in 1962, John Lainsleigh detects a 10 to 20 electron volts particle in Volcano Ranch. And it seems like there was no end to this cosmic ray spectrum, except that in 1966, something dramatically new happened. Penzias and Wilson discovered the cosmic microwave background, and we will see at the end of the lecture that what this implied for the origin of cosmic rays. Just in passing, I also want to note that now we know that cosmic rays have a lot of implications for a bunch of different things. First of all, they are one of the main responsible for DNA mutations on Earth, and they certainly contributed to create the conditions for evolution in one way or another. Now, take into account that in normal conditions, the cosmic ray radiation dose is about 30 millirem per year if you are at the sea level, versus about 8 millirem for a chest X-ray. And of course, the situation gets dramatically worse if you are higher on the sea level. And in fact, pilots of airlines have a special insurance because of damage caused by cosmic ray radiation, because they suffer an exposure to cosmic ray radiation which is much larger. And of course, the dramatic change is really for space travel. If you go outside the atmosphere, the level of exposure becomes much higher. And not only that, but you are more exposed not only to standard cosmic rays, but also to cosmic rays from the sun. Now, the level of radiation that is needed for traveling to Mars, for instance, mission to Mars is 6 months to go, 6 months to come back. And then, of course, once you go to a party that far, you want to stay for a little bit. So if you stay for, say, a few months there, the level of radiation that you accumulate on the way there and back, plus the staying there, is roughly the lethal one, which means that you have to find a way to get rid of this irradiation if you want to get to Mars, okay? So for sure, cosmic rays need to be, maybe that's why they keep giving us money, right? I don't know, but certainly they do have an effect on long time space journeys that we need to understand. And of course, it's going to be much worse if one day, very far from now, we leave our solar system. Because our solar system, we'll see in a second, is protected from cosmic rays from the solar wind. And if there is no solar wind, then you get hundreds of times more radiation. And that's, again, it's something that you don't want to. You remember the ionization of the electroscopes? Well, this phenomenon is terribly important for a bunch of other phenomena. For instance, it is known, you must have seen these beautiful images of star formation regions. And in these star formation regions, you see these bright things, which are the stars that are being just turned on by nuclear fusion. But the star formation is actually regulated by the level of ionization in the cores of molecular clouds. There is absolutely nothing that can penetrate the center of these molecular clouds, with the exception of cosmic radiation. Cosmic radiation are the only ones that are deeply penetrating and can get ionization in the center. And that's the place where you start forming the stars. So the ionization is crucial for star formation. And of course, stars, once they start, they die, as everything else. And the death of stars we will see through these lectures that lead to the formation of cosmic rays that in the end lead to the ionization that blah, 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 and the cycle repeats. So the system is, looks like it shows evidence of self-regulation. One thing in terms of terminology, as I told you in the very beginning, all the phenomena we will be discussing about are absolutely general, and you can apply them supernovae as well as gamma ray bursts or clusters, whatever you do in your life, the same kind of physics apply. So maybe it is a good thing to keep in mind that usually when we talk about cosmic rays, what we mean is the non-thermal particles that manage to get to the Earth. In general, we talk about accelerated particles if these are particles that stay inside the source or don't manage to get to the Earth. So there is a little bit of a distinction to make in terms of terminology. Now, this is the guy. This is the spectrum that has evolved in about 100 years of history of measurements. This is the flux of cosmic rays, the so-called all particle, namely when you ignore what you are seeing and you just sum up everything together. But as you see, this is a spectrum of protons. This is a spectrum of all particle. So most of them are really protons plus helium and a little bit of carbon and oxygen. But most of it is really protons. And the spectrum of cosmic rays extends out to about 10 to 20 electron volts or so. And you see that after that energy sort of drops down. And here you see a lot of more components because we got really good with measurements. So now we measure protons, helium, carbon, all the nuclei. But we also measure electrons and positrons, antiprotons, and so on and so forth. The spectrum looks like going down with energy. So energy is here, flux is here. So it goes down quite fast. This is multiplied by the square of the energy. Okay, so this is actually going down roughly like e to minus 3. And there is some feature here which we call the knee of the spectrum. Here, there is another feature here which is sort of the end of the spectrum of so-called ultra-energy cosmic rays. And there is a little bit of a feature here down in the 10 GeV range, which is actually associated with solar modulation, namely the fact that cosmic rays, when they have sufficiently low energy, they cannot penetrate inside the solar system. So you have the sun here, you have the Earth somewhere here, and there is a wind of protons, high-energy protons that travel at about 500 kilometers per second from the sun. And at some point here, there is the interstellar medium, which is standing. So the solar wind impacts on the interstellar medium and eventually produces a transition region. Now, the fact that the wind is expanding in this way with its own magnetic field, you can imagine now a cosmic ray particle that tries to enter the system, tries to somehow move with the wind itself. So it is trapped somehow in the wind, in the magnetic field of the wind. So it starts rotating, and if the wind and the advection velocity of the particles are comparable, sooner or later the particle is reflected back. And so this is called a solar modulation. And it basically implies that particles with energy below about 10 GeV or so really is not able to penetrate the solar system. That's of tremendous importance for the evolution of life on Earth. If we didn't have this phenomenon, it would have been impossible because the level of radiation would have been unbearably high, okay? So the fact that the solar wind stops this radiation from coming through has been crucial for us as human beings. And of course, it will be crucial also if one day we'll be able to travel outside the system, because we will have to find a way to get rid of this huge level of radiation. But again, this is a problem also if you move inside the wind. As I told you, to go to Mars, already the level of radiation is close to the lethal one. And people are investing a lot of money to actually find a way to get rid of this radiation. It's actually interesting because 10 days ago, I was asked to give an interview on the moon landing because of and so I had to study myself some of this stuff because I don't work on space exploration, right? And I found a lot of interesting things. So for instance, people have thought about mounting magnets all around the spacecraft so that you activate the magnet and the particles are reflected out and the astronauts are safe inside. But it costs a humongous amount of money and energy to have that, because roughly it's about 10,000 euros per kilogram of stuff that you put on orbit, and that's unbearable. Another way is to turn on an electric field. So you charge your spacecraft, and so you reflect electrostatically the particles. But again, also turned out to be unfeasible on energetic grounds. So the only way that is left is really to protect the astronauts by having a layer, but of course that costs a lot of money. You don't want to have your spacecraft made of lead, right? So interestingly, the most feasible thing that people have thought about is to construct walls in which there is fluid. For instance, the water that the astronauts are going to drink might be in the walls and they can absorb the cosmic rays. But of course, you drink the water, right? So you can imagine already where we are going here. So you want to recycle the water. Okay, so anyway, this is just a byproduct. This again is a picture like that of the solar wind. And the only reason why I did this is because in 1977, when I was a little kid, people sent a spacecraft in the solar system, which was called the Voyager. Actually, it was two spacecraft, Voyager 1 and Voyager 2. And a few years ago, the Voyager 1 actually escaped the solar wind. So now it is in the interstellar medium. It's way out here. So it's where the real cosmic rays are. And interestingly, it's sending us still the flux of cosmic rays that it's measuring, okay, after 40 years or so. It's still sending data. And now we know actually how the spectrum of cosmic rays would look like if we could observe it. So now we have actually direct measurements. It is so damn far that it's about 20 billion kilometers, and it takes 18 hours for light to reach us. So every time that you have to tell something to the satellite, you have to wait 18 hours to go and 18 hours back if you want to turn it or do any other kind of thing. Of course, by now, all the instruments are almost shut down, almost all shut down, because all spacecraft was fueled with a plutonium battery. It was the last example of atomic energy used in space. Then there was the famous Treaty of Americans and Russia that did not allow usage of energy in space, and therefore the whole program, now it's not allowed anymore to use plutonium out there. Okay, so now let's start talking about some things that are more connected with the real lectures. So first of all, we know now that particle transport in the galaxy is all but trivial. And how do we know it? Well, we know it because of the observation of a few things that we call cosmic clocks. In other words, you see that plot up there, that's the abundance of elements in the solar system, that's the blue, and the black is the abundance of the same elements in the cosmic radiation. And as you see that, more or less, with a few exceptions, but more or less, they are consistent with each other. But then you see two huge anomalies. One is that the lithium, boron, and beryllium, which are these three things here, these three dips here. This is like 7 orders of magnitude difference, and a little bit of dip here. Now, the reason why it's so interesting is because lithium, beryllium, and boron are three elements that you might know the universe did not manage to form because of Big Bang nucleosynthesis, right? The universe became too cold, too fast for forming these elements because of merging, fusion of lighter elements. So how is it that in cosmic rays you have so many of them? And the only way that you can is because you are breaking heavier things. Well, of course, the heavier things is not a big deal. You form them in stars. So you have carbon, you have oxygen because of star formation. And eventually you inject these things in the interstellar medium. But why do I have these three elements which are not formed in the star formation, or they are destroyed as easily? Well, there is a process called spallation, which basically means that you have a big nucleus hitting a cosmic gas, protons, for instance, and then ending up in a lighter nucleus. This process usually conserves energy, which means that the energy conserves the Lorentz factor, which means that the energy per nucleon is the same in the beginning and in the end. Okay, so if this is what we will call a secondary nucleus. Well, if you have a nucleus like carbon, for instance, a carbon interacting with a nucleon in the interstellar medium can lead to the formation of boron plus another nucleon. And so you, plus n nucleons, plus other stuff. Okay? So you form boron with a cross-section that is proportional to the mass number A. To some power 0.7. This is important because by measuring how many nuclei of boron you find, you can actually measure how long the cosmic ray was in the region where it produces that. The reason for that is that you can define a time scale for this process, which is 1 over the density of gas and the speed and the cross-section. And you measure it, and it's about 100 million years. 100 million years. Why is this number weird? Because when you take the size of our galaxy and you divide by the speed of light, typically you get numbers of the order of thousands of years. Thousands, not 100 million. Therefore, the transport of cosmic rays in the galaxy cannot possibly be ballistic. In other words, a particle cannot go straight or even do orbits, helix. It has to have a much more complex trajectory, and that's why people thought that the motion of the particles in the galaxy is well described, perhaps, by diffusion. And this is what Pasquale will illustrate, I believe, tomorrow, and we will see it many times throughout this course in different ways. There is a second type of observation, which is associated with beryllium, and not only beryllium, but others as well, aluminum-26. Beryllium comes in 3 isotopes. Beryllium-10 is unstable with a lifetime of a few million years, and you see in laboratory when you have an accelerator and you shoot stuff on a target, you produce the 3 isotopes more or less at the same amount, with the same proportion. So you have the 3 peaks roughly at the same height. And here, in cosmic rays, the 3rd peak has basically gone, which means that the beryllium-10, which is unstable, is actually staying in a galaxy for a time that is comparable with, actually larger than its escape time. So you're basically seeing the exponential drop in the decay of beryllium-10. Again, it looks like cosmic rays are staying in the galaxy way longer. So this piece of information is the same as before. It's just an alternative way of looking at the same phenomenon. Okay? The first time, we're looking at it through the production of secondaries. In the second instance, you look at disappearance of something which is unstable. But the kind of information that you access is basically the same. Unfortunately, both these measurements have been done at very low energies, where many things can go wrong. One of them is this guy here. Okay? So only recently, people have measured with the AMS-02 satellite, not exactly the beryllium-10, but the ratio of beryllium to boron. Why is this important? Because beryllium includes all the elements, the 3 peaks, beryllium-7, 9, and 10. So if there was no decay, this ratio, beryllium over boron, would be absolutely flat and then go slightly up only because boron is a little bit heavier and it's being broken by spallation a little bit more. Therefore, you are decreasing the denominator of this fraction. Not only that, but boron breaks by this process. Okay, that's the essence of the black. You don't see it. So boron, through this process, breaks into beryllium, which is the numerator. So you decrease a little bit the denominator, you increase a little bit the numerator, it should go up. You measure it and it goes down, and most likely this is because the beryllium-10 is disappearing by decay. These very recent measurements, I'm not even sure this has been published. But anyway, I mean, it has been presented in. Okay, so I think we can skip this. I already told you. And these are the comparison timescales. This is the size of the galactic disk. It's about 300 parsec. Timescale corresponding to that, 3,000 years. So roughly, the ballistic timescales are of the order of thousands to tens of thousands of years, but the ones that you measure are hundreds of millions or tens of millions of years. Okay, so of course, while these cosmic rays are moving around in the galaxy, as I told you in the very first few slides, they also produce radiation because of processes similar to those, but inelastic. So for instance, you may have that a cosmic ray proton interacts with another proton and leads to the production of pi plus and pi minus plus anything, or you're looking at electrons that are moving in the magnetic field and produce synchrotron photons, and so on. So, for instance, this is a picture of the galaxy, how it would look like in the radio band. And you see that an electron, if you want to have a gigahertz photon due to this process, you need an electron with energy about 16 GeV. So we're talking about relatively low energy. I think that Pasquale will cover this in quite big detail. And the time scale for this process is of the order of 1 billion years divided by the energy of the electron. So at this point, for instance, you can check what's the extension, the physical extension of the radio emission by calculating how far the particles diffuse in a time of loss due to the process we just mentioned. And this typically is of the order of kiloparsec divided by the energy to some power. So that means, again, that the extent of the radio emission gets smaller when the energy goes up because the electrons die quickly, right? The more they lose energy, the more they die, so they cannot get far away from the galactic disk. So in principle, you can look for these kind of effects to figure out how cosmic rays get transported in the galaxy. By the same token, you can study the gamma ray emission. This is the gamma ray emission from our galaxy. You can see very clearly the disk of the galaxy, while in the radio, you see a very extended region. The reason is that the magnetic field is everywhere in the galaxy, so you see emission from a lot of places, but the gamma ray emission is actually produced by this process here, mainly with pi zeros here. And, oh, that was it, right? Yes. So it is produced by pp that goes into pi 0, decay of pi 0s into 2 gamma rays, provided the energy of the proton is larger than 290 GeV. And so that's the reason why you see the gamma ray emission basically where the gas is, where the target for this interaction is, which is the galactic disk. Now, gamma ray emission, of course, is produced also, as I said, by many other processes like electron-Bremse-Strahlung, inverse Compton scattering on all the photon backgrounds and so on. But again, this part will be covered by Pasquale Serpico. The same identical processes are also the ones that take place inside the sources. I told you in the beginning, there are two issues that we will have to deal with: accelerating, transporting. Accelerating, transporting. In the accelerator, we will see that the kind of physics that is involved is really the same as the one involved in the transport. The particles need to be confined in the accelerator for as long as possible. By the same way that particles in the galaxy need to be confined in the galaxy for a very long time to explain the abundance of boron, for instance. Okay? So when you see a source, these are real pictures of, in this case, it's a Tycho supernova remnant in the radio, and the X-ray, and in the gamma rays. And all these processes are exactly the same that we see on galactic scales. It's just the parameters that change. But once you understand the essential physics, you understood it all. So these are not different questions. These are the same questions from the physics point of view. Then you can apply it to the emission in the galaxy, in the supernova, in your kitchen, whatever you want, but the physics is exactly the same, exactly the same. So that's why I said in the very beginning that there are two big questions, and once you understood those, you are a good way down the road. So I showed you radio, X-rays, and gamma rays. Interestingly, people have been now looking at supernova remnants in the optical with instruments like Hubble Space Telescope, and more specifically to something that probably we will not have the time to talk about, to discuss, but if you are interested, please stop by during the school or after, and we will talk about this. This is the so-called Balmer emission. So it's a 3-to-1 transition in the atom of hydrogen, and it's a beautiful type of observation. So this is supernova 1006, and this is actually a tiny piece of the shock here, zoomed in. These are scales of the order of about 1,000th of a parsec. So it's unbelievable. These observations are actually looking at the very fine structure of the shock surface. And by studying these, you can actually measure in a colorimetric way how much energy in the form of cosmic rays is sitting close to the shock. It's beautiful type of observations. Unfortunately, these kind of observations are possible with telescopes like this, but for the future, because these telescopes are used for cosmology mainly, for high redshift, that means you want to see infrared light because it's redshifted. So most of the future telescopes will be unable to look at these things. Okay, some numbers because I want to make some points here. You will learn tomorrow with Pasquale of diffusion and how it's explained in terms of microphysics. Why do we need microphysics in the first place? Well, because remember that the gyration of a proton of 1 GeV, just a miserable proton, in the magnetic field of the galaxy, a microgauss or so, is of the order of 1/10 of the size of the solar system. It's a ridiculously small radius if you compare it with the size of the galaxy, which is tens of kiloparsec. So that's why it is so damn difficult to understand the physics of this propagation, because the microphysics is on small scales, and what you see is on kiloparsec scale. So you better have a good way of relating the two to each other, because otherwise you make very slow progress, and perhaps that justifies the fact that it's 100 years that we are looking for the sources of cosmic rays. But also, it's telling you something. When I arrived in Chicago in the end of the 90s, David Schramm just came out with this paradigm of inner space, outer space, and he put it forward to discuss about something else, namely the fact that sometimes, in order to understand the evolution of the universe on a big scale, you need to know particle physics. You need to know the physics on very small scales. So in a sense, this is a very similar conundrum that exists in our case. It's the microphysics that is actually determining what happens on a macro scale. In the same token, in the case of cosmic rays, again, you're looking at the galaxy or the sources on very large scales, but the relevant physics is taking place on very small scales, where interesting things related to plasma physics and particle physics are taking place, are happening. So in both cases, there is a connection between this small inner space and the big outer space, and the two are talking to each other, and that's why the problem is so complicated to handle, and that's why you're here and you have a job, or you will have a job at some point. So the idea is that you have charged particles that move in a magnetic field that at the zero order is some magnetic field line, but immediately after you have to assume that it has a small scale structure. So you have a lot of microstructure in the field. Pasquale will discuss this. And it's the interaction of this with these two that leads to the process of diffusion. But now the point is that at the same point, in the same moment, these charged particles, in doing this thing, also produce a bunch of instabilities which are connected with the plasma in which they're moving. And these instabilities change these two in such a way that they change diffusion. And diffusion, in turn, changes the charged particles. So the problem that you want to solve is a damn difficult problem, because the particles that are moving in the system are actually changing the system in which they are moving. And that's one of the things that we will have to deal with. And again, all this interesting physics here is taking place on very small scales, but then when you look at the phenomenon, you are looking at it on very large scales. So you have to find a way to connect the big ones to the very small ones. In the same way that you look at the universe expanding, and then you want to derive the equation of state of dark energy, which is stuff related to the particle physics, to microphysics world. Now, I want to spend just a few words on what happens when you keep increasing the energy of the cosmic rays. We have seen that there are many processes of energy loss. We discussed a little bit of the Bremse-Strahlung and inelastic interactions and so on and so forth. And then at some point, the particles become so energetic that it is difficult to imagine any process inside our own galaxy responsible for the production of these particles. And that's when we start talking about extragalactic cosmic rays. So at some point, these cosmic rays are not even produced inside our home galaxy, but somewhere else. And they have to propagate on cosmological distances to reach us. And we do see them, so it means they reach us. So what happens to them? Well, this energy of, I have no battery here, or almost gone. So this is the energy, the logarithm of the energy. This is the logarithm of the loss length of these cosmic rays. So on how much distance they lose half of their energy. Now you see that when the energy is below 2 times 10 to 18 electron volts or so, for a reason that Pasquale will tell you tomorrow, they mainly lose energy because the universe is expanding. So this is the same as the redshift. It's exactly the same kind of physics. So a particle is moving in the universe is expanding, so of course it loses energy because of the expansion of the box in which the particle is sitting. At some point, around 2 times 10 to 18 electron volts, something interesting happens. And this something interesting is this process here. A proton sees a photon of the cosmic microwave background. In the reference frame of the center of mass of this interaction, there is enough energy to form an electron-positron pair. At this point, you activate this interaction. From the kinematic point of view, it is allowed, and it is called the Bethe-Eitler process. And you see that the particle starts, from this point, starts losing energy because of the production of electron-positron pairs. And it keeps going down, and of course the energy loss is roughly the size of the universe below that. When you go above threshold for pair production, it sharply decreases, and then at some point, which is around 5 or 6 times 10 to the 19 electron volts, another process becomes kinematically allowed. A proton moving through the cosmic microwave background, relic of the Big Bang, is such that in the center of mass there is enough energy to form a pion, 140 MeV, and it will. Now, the interesting thing is that the inelasticity of this process, namely how much energy you lose every time you interact, is of the order of well, anyway, it's the ratio of the mass of the electron to, huh?
You adjust your hand around it and keep your index finger a little bit backward.
It's the energy of the mass of the electron divided by the mass of the protons, which is 10 to the minus 3. So you lose energy slowly. But here, it's roughly the ratio of the mass of the pion to the mass of the proton, which is 10%, 20%. Therefore, this process has a larger inelasticity, which means that the particle loses energy very quickly. And so you see that at this point here, what happens is that the proton starts seeing the tail of the cosmic microwave background, the higher energy photons in the cosmic microwave background. And it starts losing energy, and then it keeps growing. The path length keeps getting smaller, and at some point here, you're starting the peak of the cosmic microwave background. And you see that at this point, the loss length is of order 10 megaparsec, which on cosmological scale is nothing. It's very small. Now, this tremendous suppression, so you see that here the path length goes from a gigaparsec to 100 megaparsec within a factor of less than 2 in energy, means that at that energy, you can only see sources which are inside that range of distances. So all of a sudden, within a factor of 2 in energy, you switch from seeing almost all the universe to just seeing your cosmic neighborhood. And this is what goes under the name of Greisen-Zatsepin-Kuzmin cutoff. The reason why the spectrum of cosmic rays should drop very quickly at around 10 to 20 electron volts is exactly associated to that. Now, that is for protons. For nuclei, there are different processes that kick in. You will look at these observations, I think, next week, right? Observation of ultra-energy cosmic rays. I mentioned the nuclei because the most recent observations of the Pierre Auger Observatory seem to show that the composition is mixed with heavy nuclei at very high energies. So you have to deal with processes like photodisintegration in addition to the Bethe-Eitler that we have already studied, and in addition to the adiabatic expansion of the universe, the redshift, as we said. But interestingly, because nature is evil, the place where the interesting physics appears, namely where the suppression in the flux is expected, because of completely different processes, is roughly the same, of course, just to make our life easier. And so around 10 to 20 electron volts, 10 to 19, 10 to 20 electron volts, you see that there should be a feature in the spectrum of ultra-energy cosmic rays, both in the case in which they are protons or nuclei, although the physics is completely different. And you will see, I don't know if somebody's talking about the transition from galactic cosmic rays to extragalactic cosmic rays, but this kind of processes reflect, of course, in where and how the galactic spectrum of cosmic rays ends and eventually the extragalactic spectrum starts. Now, for ultra-energy cosmic rays, the important things to keep in mind, the reason why I'm putting this slide, is because there are simple considerations that you can make. For instance, impose that even at the highest energies, the Larmor radius of the particle must be smaller than the size of the source, okay? And this translates into a bound in the luminosity of the source. Why? Well, because if you put this on the other side and you square it, B squared is the energy density in the magnetic field. And energy is conserved, so if there is magnetic field, it must come from the kinetic energy, which is 1/2 of rho u squared. We will see this later in the course, why. And so when you multiply by 4 pi r squared and you use this bound, you deduce that if you want a particle to be accelerated at energy 10 to 20 electron volts, the luminosity of the source must be at least 10 to 45 ergs per second. And that's a huge luminosity. So in other words, we're saying that when you go to these tremendously high energies, the sources that you want to speculate about or model or whatever, they are extremely powerful or transient. So gamma ray bursts, active galactic nuclei, this kind of stuff, which of course will be discussed and covered by other speakers. But again, the physics that will be involved, even in the acceleration of these guys, will basically be the same. I don't have time to cover this. And of course, we have the prime actor at the present time, which are neutrinos, which of course can shed quite some light on the sources also of ultra-energy cosmic rays, and not only because of the emission from the sources themselves, but because of the sum of the contribution of many sources to the so-called diffuse background, so the diffuse flux of neutrinos and gamma rays that come from the universe. An interesting application of this is this plot. This is the flux of neutrinos that we have detected. This multiplied by E squared. And this is the flux of diffuse gamma rays that we have measured. OK, so as you see, these neutrinos, if you trust the spectrum that you get here, and you extrapolate down here, and you say that for each neutrino there was also gamma rays produced, well, you are in big trouble, right? Because we don't see those gamma rays at low energy. Even if there was no gamma ray produced at this energy, really, the gamma ray produced at even higher energies and propagating through the universe. I'm not sure if some of the speakers will cover the cascading processes, but the cascading of gamma rays to lower energies through pair production and Compton scattering would lead to a flux of gamma rays roughly at this level, which people doing these kind of observations claim that they know where comes most of the flux of diffuse gamma rays, blazars. And if you trust this kind of information, then there is not much room left for any other source of gamma rays, including the gamma rays that come from the emission from the cascading from such high energies. So again, even just by studying the diffuse emission and the neutrinos together, in principle, you have valuable information about what is going on. And of course, there were gravitational waves. Gravitational waves have particular impact on this field from the point of view of neutron-star merger, because they are the ones that have also a counterpart in electromagnetic radiation, perhaps in cosmic rays, but we didn't detect any of it yet. And they are going to be source of more information in the future. Now, for your own future instead, I'm almost done. For your own future, on the other hand, I think you need an objective indicator of how dynamical the field is, because that's more or less proportional to the probability for you to find a job. And I think it is pretty good. It looks pretty good, because there are plenty of experiments in the field of high-energy astrophysics that are being started at the present time, or that just started, or they will start in 10 or 20 years from now. So that's good news. For instance, in the radio band, there is Ka and some precursors, LOFAR. There has been quite an effort in measuring the polarization of X-rays with XIPE. There are numerous experiments that either are flying, like AMS-02, Calais, Ice Cream, Nucleon, and DAMPE. All of them will measure the spectrum of cosmic rays in the galaxy up to almost to the knee, well, within a decade or so to the knee. And soon we will have another two starting, HERD and LASSO. This is another satellite. This is from Earth. It's a shower experiment in China. And in the future, people are already thinking about the successor of AMS that they're naming AMS 100. Is it terribly science fiction-ish kind of experiment for now? It's going to be put in L3, and well, anyway, it's terribly fascinating. CTA, as Fabio mentioned, the Cherenkov Telescope Array is already being built in the southern hemisphere, so it's probably the major high-energy astrophysics experiment in the future. And of course, IceCube and the successors will be measuring and keep measuring the flux of neutrinos, hoping that at some point there will be evidence for some source of neutrinos instead of diffuse flux of neutrinos. In the ultra-energy part, in addition to the Auger Observatory and the telescope array, people are thinking about going into the future with some experiments which are mainly in space. Use of PBS is a balloon experiment, actually, so almost space. And POEMA is another extremely futuristic experiment, a couple of meters of mirror in about 400 kilometers height, looking at the showers from above. And all of these, of course, will need a lot of brain power and a lot of manpower. Just a quick feature scheme of the remaining lecture. So today it was fun, but tomorrow will start to be a little bit of work. So tomorrow we'll look at Blasi equation and what we can, how we can transform the Blasi equation in what we call the MHD, magnetohydrodynamics. That's important because for the first time, for some of you, you will hear things like Alfvén waves and magnetosonic waves and how you derive them. And this will be very important in the final part of the course. And then we'll switch to the actual usage of all this stuff, of this technical stuff, for accelerating particles. In the end, that's what we want to do in this lecture. We want to kick particles to very high energies, and that's we will learn how to do that through the standard processes. Some are slow, some are faster. We'll try to understand how to treat both physically and mathematically this problem of particle acceleration. Okay? And then, of course, as usual, you develop a theory and then you criticize it. That's how it works in physics. And then how to make progress. So you will build a theory and then we'll show that it doesn't work so that we can move forward. And so we'll move to a little bit of a more detailed version of the same theory in which I will try to convince you that we understood some of the basic physics that really lead to the acceleration to very high energies. And then, of course, I will discuss some applications of this physics to, for instance, supernova remnants, and I'll discuss some issues related to the escape of particles from the accelerator, namely when they switch from being accelerated particles and when they become cosmic rays. And if I have time, I will discuss a little bit of diffusive shock acceleration in partially ionized medium, which is that thing that I mentioned you before with the Balmer lines. That it's very interesting. But again, if some of you is interested, just stop by and ask questions. And for now, I will stop here and leave room for the coffee break, I think.
Thank you very much, Pasquale, for the amazing...
Questions?
Yes, we have time for 1 or 2 questions. Don't be shy.
I will not leave until I get at least 3, so if you want to get coffee.
It's just, do you have any idea of what causes the knee feature in the cosmic ray spectrum, or is it
we
an
go
open
on
question?
the heavy stuff now, huh? Okay. So an interesting piece of observation is that around the knee also, you see this feature, but you also see a change of the mass composition of the cosmic rays. So you see that they're becoming a little bit heavier. So we don't know at the present time even whether the knee is dominated by protons or helium or something else, okay? It would be precious from this point of view to see the spectra of the individual elements, protons, helium, carbon, oxygen, up to very high energy. But it's, of course, because the flux is going down, it becomes harder and harder to make this measurement, right? So we will have to need a little bit of more time. But the idea is that if you have a situation like this, so let me say that this is e to some power times the flux. I don't really care what that power is. It's whatever power it needs to be to look it flat, okay? So let's say that the proton spectrum looks something like this. And of course, it must have some maximum energy at some place where the accelerator runs out of steam, right? And then maybe you have helium. Now, the flux of helium, we know that at low energy is lower. But we will study during the course that the maximum energy in an accelerator scales as Z, the charge of the nucleus. So if you have a helium nucleus, which has a charge 2 compared with the protons, then the maximum energy of helium must be 2 times the maximum energy of protons, right? So it must look something like this. And then you do it for the other elements as well, and it must look something like this. So it happens that when you sum all these components, you invariably get something that looks like this. So an E naturally comes out when you overlap components which have different mass composition, different mass number. Whether this is the right explanation, again, requires a measurement of the individual elements. And just to give you an idea of how difficult this is, there are so far 2 experiments that measured the flux of protons in the region around the knee. One is Argo, and the other one is Cascade. And they see a position of the knee of protons. So this guy here, this part here, which is a factor of 4 difference. Just to give you an instance of how difficult it is to make this measurement. The flux is going down very quickly. There are systematics. Moreover, for experiments which are on the ground, you have to correct for how well you know the cascading process in the, in the atmosphere. So it becomes complicated. So far, we don't have this level of observation yet in the region of the knee. Down here, we have beautiful observations. And actually there, it's the systematics that dominate the error. The statistics is overwhelmingly good. But this is one possible reason why we see a knee in the spectrum. Another question. We have to get to 3 to get to the coffee break. There's one here. Oh, you don't want him, I see.
You were asking a question? Yes?
So far, what is the most accepted source of extragalactic cosmic rays, which are ultra high energy, right?
There is no accepted. There is no accepted model that I know of ultra energy cosmic rays.
Mm-hmm. And is there a way to know the composition of?
Sure. I don't think I have a. Do I? I'm not sure I have a slide with. Well, somehow I have a little bit of it here. So the information about mass composition that we have comes from the Auger observatory, and it's a little bit of an indirect observation in the sense that what you do is to study the showers of the induced by cosmic rays inside the atmosphere. Okay, so. During this lecture, I will always try to explain to you the physical problem, the physical essence of the issue, and then try to describe it. There are 2 different stages. Usually the first one is very important because it tells you also where to go later. So take a ball, like a proton, and then take a ball that is 56 times the initial ball, right? So the first one has much more probability of interacting, right, inside the atmosphere because it's bigger. So if you have a proton or a heavier nucleus, you can expect that how deep the particle penetrates in the atmosphere depends on how big the particle is, right? So you know that for a proton and an iron, these two quantities will be different. Now, this has been known for quite some time. Not only that, but unfortunately, however, we'll see, I'll come back to this. So they interact in a different way. So they penetrate deeper in the atmosphere by different amounts. How different? Well, that's the problem, right? Because if you take 2 average showers, you know exactly what will happen. Unfortunately, there are no 2 average showers in the sense that you measure hundreds of them, and then you try to describe for each one of them where is the penetration depth in the atmosphere, and the spread in how deep they penetrate overlap between the two. So it's very difficult to identify a proton from an iron on a shower-by-shower basis. You have to collect many of them and then statistically try to understand how many of type 1 or type 2 or type 3 or type 4 or type 56 showers there were. This is one piece of information. The second piece of information, you can ask, how much do they spread? I mean, if you do the distribution of these showers, we said that there are fluctuations, right? So how thick is this fluctuation? Okay, so what would you expect naively? If you have 1 ball, or you have 56 balls in your nucleus, which one will fluctuate more? The one. Yeah, because in the other case, it's like averaging over 56 balls. So you're already averaging, in a sense, more on a nucleus of iron. So the fluctuations on a collection of n balls will be smaller than the fluctuations on 1 ball. So we know that the fluctuations on showers induced by nuclei of iron, for instance, is going to be narrower than the distribution of showers induced by protons. So this is something, both of these things have been studied with the Auger Observatory, and they presented convincing evidence that the mass composition at energy above 10 to 19 electron volts is getting heavier. In other words, you don't only have protons, but you have heavier elements based on these 2 ingredients. Now, this, of course, makes life very complicated from the physics point of view, because now you don't have to model just one spectrum, the spectrum of protons. Now you have to model 56 spectra from protons to iron, right? And when you try to do that, you get something a bit surprising. What you get is that you must have injected these cosmic rays, wherever it was that they were injecting, for now, don't care about that, with weird features. Namely, their spectrum should be extremely hard, like E⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ steep, steep spectra which are so flat, so hard. Okay, so that's one of the reasons why there is no accepted model, because we cannot figure out why the spectra are so hard. Okay, it gets even worse, because after you make a lot of work with all those lines trying to be going through the data, you are forced by modeling to add by hand a spectrum of protons with a completely different spectrum. Very steep this time. Now you understand that this is very ugly. I mean, from the scientific point of view, many people, including me, have stopped working on the problem because it became really very complicated, but complicated not in a good way. Complicated in the sense that it became too meteorological, how to say, I mean, too messy, epicycled. So, but just to respond to your question, no, there is no accepted model. There are some good ideas, like for instance in so-called unipolar inductor. So if you have a neutron star which is fastly rotating around its axis, the spectrum that you get from this kind of source is easily mass loaded. So there is heavy stuff, because the surface of the neutron star is dirty with iron nuclei. And it's also very hard. It's like E⁻⁻⁻⁻ spectrum. So in principle, neutron stars are one of the possibilities that have been studied and investigated in this context. But it's not by any way, an accepted model in the sense that everybody knows it's the right model. It's just an idea. Okay, we are one question away from the coffee break.
Yeah. Maybe you want to go? Quick question, quick answer.
No, it's just a curiosity. You know, you said that thanks to the Voyager, we can know the spectra and lower energies. Mm-hmm. How is this spectra in that part? How is the spectra in that part?
It's almost, it's basically an E⁻² spectrum with a little correction. So it's exactly what you would expect if cosmic rays were traveling through the galaxy through advection and with the effect of energy losses due to ionization. So it's a pretty straightforward, I mean, it's interestingly trivial in a sense. But it's a good piece of information because there is a lot of ambiguity in the models that you use at higher energy based on what we didn't know about the low energy. So this definitely helps. It's weird now that something that was launched 40 years ago is representing a source of major news today.
Okay, so I think we can thank Pasquale again for the wonderful lecture. And so there is coffee break upstairs. If you haven't hanged your poster, hang it now. And I will ring a bell in 15, 20 minutes to come back for the other Pasquale's class, okay?